Hello, everyone. Welcome to a new edition of our High Energy Astrophysics Division seminars, Wednesdays. I'm very happy today to introduce the speaker, who's Brian Williams. A little bit of background for him. So he got his bachelor from Florida State University, PhD from North Carolina State University with Steve Reynolds and Kazi Borkowski. He was then NASA postdoctoral program fellow at NASA Goddard, then super scientist at the Space Telescope, and then back to Goddard. His current position is NASA project scientist for the mission Chrism, and is also chief scientist for the Physics of the Cosmos program office at NASA. He specializes in data analysis and modeling of the X-rays supernova observations. And even if he's not going to talk about mostly this today, just a quick reminder, feel free to write questions in the chat. We will read them out at the end of the presentation. So the title of the presentation is Prism, X-ray imaging and spectroscopy mission. Brian, the floor is yours. Thank you for being with us.
Okay, well, thank you, Federico, for that introduction. Obviously, I wish I could be there in person. As I was being introduced, I was just scrolling through the participant list, and obviously, I know many of you. I hope to see many of you in a couple of weeks at the head meeting, since we can't be in person today. But yeah, I'm here to give a mission status update on the X-ray imaging and spectroscopy mission, which we do pronounce Chrism. It's one of the most common questions I get is, how do you say that word? Is it X-Prism or Srism? We say Chrism. So if you take nothing else out of today's talk, then you at least learn one thing. So, oops, let me advance. So what is Chrism? Well, it sort of occupies the other end of the parameter space from a mission like Chandra. Chandra, of course, is a high spatial resolution mission. We are a high spectral resolution mission. So Chandra can make pictures like this at the top left of Kepler's supernova remnant. The spectra, though, look like that, whereas Chrism, we're not going to make a nice, pretty picture, but we will produce a spectrum that looks something more like this. So we'll be about 2 orders of magnitude better spectral resolution than the CCDs on Chandra or XMM. So the real quick overview summary of the mission is that it's a JAXA-NASA collaborative mission. There's also an ESA participation. We have 2 instruments on board. Resolve is sort of our workhorse instrument. It'll be a soft X-ray spectrometer that'll provide spectra like the one I just showed you. You can also see down there on the left, that's from a previous mission, which I'll talk about. Our other instrument is called Extend, and that's about a 40 arc minute field of view soft X-ray imager. We are scheduled to launch in Japanese fiscal year 2022, which runs through March of 2023. The goal of the mission is to recover the science lost with the demise of Hitomi in 2016. I'm sure some of you will remember that when this mission first was approved a few years ago, we were called CHARM, X-ray Astronomy Recovery Mission. We've since changed the name to Chrism. And after our initial checkout and guaranteed time phase for the science team, the rest of the mission lifetime will be for general observers. So an outline of today's talk, I'll first talk about the history. How did we get to where we are today? I'll talk about the technology involved in making a mission like this, and I'll show some cool hardware pictures. I'll talk a fair bit about the science, of course, since that's what I'm a scientist like all of you are. I'll then give a mission status update, literally up to the day of where we are as of right this second. What's our status and where are we going from here? And then finally, I'll talk about, I have it as Chrism and you. What I really mean by that is how will you, the general astronomical community, be able to use Chrism? What opportunities will there be? Stuff like that. So to start off with, I'm sure most of you are familiar with the fact that this mission certainly has a bit of a past. We've tried this mission a couple times before and have run into some troubles. This is a picture of the Hitomi launch from 2016. And as I'm sure everyone knows, Hitomi was planned to be a long-term mission. It was lost on day 38 to an operations mishap. But prior to that, it had been working completely perfectly, even exceeding requirements. So we hope to have the same thing here. And I'll show some results from Hitomi. We did get a few results out of it. We have about 13 science papers. Last I counted, at least, it was 13, plus several instrument papers. And you can find all of those on ADS. We really felt like someone described it to me one time as, with the loss of Hitomi, it felt like being able to glimpse the promised land, but not being able to walk in there, because we really saw the power of high resolution X-ray spectroscopy, and then we unexpectedly lost the mission. So we really felt like this is a transformational leap forward, and that's why both JAXA and NASA were willing to rebuild this mission again, because of the results that we saw out of that. So what is one of those results? Well, this is the Perseus Cluster. This is an optical image of the cluster of galaxies. When we look at it in X-rays, this is a Chandra image of the galaxy cluster. You see it's mostly just hot gas. There's sort of these bubbles of gas, and there's these voids too. So we pointed Hitomi at that, and this is the spectrum that came out. So I apologize, the numbers here are a little small, but there's 1 keV here, goes up to about 8 keV over here. And obviously this big line at 6.5 keV is the ubiquitous iron K alpha feature. So why was this so transformational? Well, if you look at this public press release image that we made out of this spectrum, we focused on the iron K line at 6.5 keV, and we overplotted that red line that you see. That's the previous best spectrum of the Perseus cluster. That was from Suzaku. So obviously, Suzaku easily detected the iron line, but it didn't exactly separate it out into its components. And those smaller lines that you see there, with chromium and manganese and some of the other lines, Suzaku either didn't detect them at a significant level or just barely detected them. So again, this is what tuning up the resolution by a factor of 50 or so gets you in spectroscopy. This is the actual image from the Nature paper that we wrote on this, zooming in really closely on the iron K line at this point. And again, in this picture, the previous Suzaku spectrum is that blue line. So this just shows again that we were able to resolve out the individual components of that iron K line. We were even able to resolve the lines themselves. The purple Gaussian curve you see there, that's the SXS response. And so the fact that we saw lines that were broader than that, meaning we actually were resolving those lines. So we were able to get the velocity and the turbulent pressure out of this and compare that with thermal pressure in the hot gas, which is something that had never been done before. So with that, again, we're not a super high resolution spatial instrument, imaging instrument, but we do have some capabilities to make images. And in fact, if you sort of plot the velocity structure with respect to the rest frame, you can get a crude map of redshift and blue shift of the gas in the Perseus cluster. And you can see that kind of down the middle, the gas is all redshifted. It's moving away from us. And then up at the top right, there's some moving towards us. So it's sort of like we're sort of detecting the sloshing motion even along the line of sight of this gas in the Perseus cluster. So just a couple of the other results that we got scientifically out of this. I'm sure a lot of you remember several years ago, there was a lot of excitement when people looked at deep Chandra and XMM spectra of not just the Perseus cluster, but of stacked spectra of galaxy clusters. And there was a possibility of maybe a line that was previously unobserved, about 3.5 keV. We did not detect that line in the Hitomi spectrum. So as far as I know, the source of that line is still undetermined. We didn't see it in Perseus though, but that doesn't mean that we won't find other unknown lines when we launch and get up to full capacity. So, and what I mean by that is this is another Hitomi spectrum of a supernova remnant of G21.5, where when we looked at the spectra, we actually saw a couple of unexplained absorption features. There's one at about 4.2 keV, and there's one at about 9.3 keV. And of course, this was weeks into the launch of a new mission, so calibration is still very much an uncertain thing at this point. So maybe this is just a calibration issue, except that when we pointed Hitomi at the crab, which is the blue line at the bottom, we didn't see those lines. So I don't have an explanation for this still. It still could have been some sort of weird calibration feature, but it just goes to show you that when you launch something that has capabilities that have never been achieved before, that you hope to find unexpected things. So I'll show a lot of simulations later on things that we think we'll find, but obviously a lot of us are more excited about the things that we don't even expect to find. So how did we get from Hitomi to Chrism? Well, we had several, we'll call them lessons learned meetings between NASA and JAXA in 2016. The US astrophysics community was very supportive of the idea of rebuilding this mission. I think basically you just show somebody the spectrum of the Perseus cluster and they can see how much science you can get out of that. The president of JAXA himself came to Washington, D.C. in September of 2016. He met with NASA headquarters. He met with Goddard management. He conveyed to us that a recovery mission was the highest priority of JAXA. So basically, headquarters instructed us at Goddard to start the process of redoing it. The scope of NASA involvement is increased in this mission. We have a little bit more oversight of some of the mission operation stuff. But basically the mission, as you can see there on the bottom, it was given authority to proceed in 2017, renamed Chrism when it became an official project in summer of 2018. So I don't think you all need this slide, but I included it anyway. The entire talk I'm giving you today is part of a colloquium that I give, sometimes at universities. I've given it to public astronomy groups. So I'll skip through these next couple slides pretty quickly. I think you mostly know how X-ray astronomy hardware works, but we do use grazing incidence mirrors. We don't use normal incidence. You can see the diagram there on the bottom right. X-ray astronomy is something where we're counting every photon. It's not infrared astronomy where you're just overwhelmed with photons. We are counting every one. And of course, that's the same image I showed earlier of a typical CCD resolution of E over DE of several dozen or so, whereas we'll be 50 or 100 times better than that. So it is possible, of course, to use do high resolution X-ray spectroscopy. The previous method of doing this, though, has been using gratings, and I show here there's an RGS spectrum on the right of, I think, a star HR 1099, and there's a HETG grating image there on the left of EO 102, which is a small supernova remnant in the small Magellanic Cloud. Again, I think you all are probably aware of this, but the downside or the difficulties of using gratings for doing spectroscopy are you're limited in your collecting area and your spectral range. It gets really difficult to do for extended sources, especially large extended sources like clusters and supernova remnants and things like that. And you have an energy dependent spectral resolution. So all of this can be overcome if we can do non-dispersive X-ray spectroscopy. And how do we do that? So this is one of my favorite slides to give, especially with people who aren't super familiar with X-ray astronomy, because it's a really easy process to describe how we do this. It's just extremely difficult to actually build the thing to do it. But basically, we just make the detector really cold, and every photon that comes in that hits the detector heats it up just a little bit, and we can measure that rise in heat and back out the energy of the photon as it came in. So if you're talking about measuring single photon heat deposits, you have to be pretty cold in order to do that, because you're depositing, millikelvins worth of temperature into there. So our entire detector has to be cooled down to 50 millikelvin and kept that cold. So again, when I describe this to non-astronomers, I always say that, you think of space as being cold. Well, for us, space is way too hot. If we just put it out there in ambient space and left it at 2.7 Kelvin, we would never be able to do this at all. We actually have to go to space and then cool our detector down by another several orders of magnitude. So we start with liquid helium that gets us down to 4 Kelvin. Then we have a multi-stage refrigeration process that every stage drops you down, another order of magnitude or so. And you can see a little diagram there at the bottom right. We're at the detector surface. The entire thing is at 50 millikelvin. We know this is possible to do because we've actually done it before. As I said, Hitomi was working flawlessly until it was lost. And this is an actual plot from Hitomi after it was launched of the detector cooling down. And you can see the time scale there. It's of order, that starts at 4 a.m. and by just before 5 a.m., we were cooled down all the way to 50 millikelvin. So we know how to do this. It doesn't mean it's easy to do it again, but we do have some experience with doing this before. And this is actually what the detector looks like itself. This is the Hitomi detector, but the Prism detector is identical in every way. You can see it being held there in someone's hand. The actual detector itself is it's smaller than your pinky nail. It's a few millimeters on the side. It's 6 by 6 array of pixels at 30 arc seconds. And this will provide the mission requirement is 7 EV. We were actually getting about 5 EV resolution on Hitomi over the soft X-ray band from about 0.4 to 12 keV. This detector was built at Goddard. It was delivered to JAXA on November 2019. It actually shipped out on Veterans Day. And it's been there ever since undergoing testing. And in fact, this is just sort of a cartoon. Starts with a real image and moves to a cartoon. But this is a little video that our public outreach team put together to show how this actually works. So you'll see the photons start to come in. Every photon hits the detector, heats it up a little bit, and then it cools back down. And again, that heat deposition onto that is what we're actually measuring. And then we're converting that back into an X-ray energy. Since we're so cold, we have a very low non-X-ray background from the instrument. And we also have an anti-coincidence detector that sits right behind the instrument to filter out cosmic rays and of charged particles that come in. So when those charged particles come in, they go right through the detector. And if they are detected by the anti-coincidence detector, then we know that wasn't a photon. So we can discard that thing. And actually our non-X-ray background is less than 1 photon per day per 10 EV bin. So we really do have an exceptionally low non-X-ray background. This is just a chart of our top level performance requirements. I'm not going to go through this line by line, but you can see some of the things that are of interest. Energy resolution better than 7 EV. We actually got about 5 on Hitomi. You can see the effective area there. The detector is designed to peak around 6 keV so that we can see that iron K alpha line. So we have more effective area at 6 keV than we have at 1 keV. And again, you can see that the requirements and what we actually measured on Hitomi, we were well exceeding those requirements. We have enough helium on board to last 3 years. The important thing, though, is that we are not limited in our lifetime by helium. When we run out of helium, we can still operate at full capabilities. It takes a little bit longer to cool it down since we have to do the entire process mechanically. So we go from something like 98% efficiency down to something like 80 or 90% efficiency. So we will lose a little bit of time, but not very much. And we really hope that this mission can last for a long time. I mean, my personal hope is I would love for us to do cross calibration with Athena, if that's possible. So here are some hardware pics, as I promised. So I assume you can see my mouse, but this opening right here is where the X-rays come in. So the mirrors would be 5.6 meters away up here, focusing down into this. The detector itself sits down here somewhere. I don't exactly recall how far, but it's down here. Most of the rest of the stuff that you see in this image is part of the cooling system, the refrigeration, the ADR, adiabatic demagnetization refrigeration system that keeps this entire thing cool. For scale, here's a couple people standing around the doer. So it's probably 4 feet in diameter or so, and maybe 4 or 5 feet high. Here's a picture of the entire thing sitting in a lab in Japan. This was from last year, I think. So this is when they were doing some integration and testing on the detector itself. And this is actually some ground calibration data that we got from the detector after we shipped it over there. So everything is looking exceptionally good on this. Those numbers might be too small for you to see, but we're getting a full width half max of about 4 EV. Now, again, this is just the detector. This has not been integrated on the full spacecraft, so there will be more noise, that comes into that, and that'll expand that a little bit probably. But the fact that we're getting 4 EV from the detector itself is a very good sign. I mentioned we have another instrument. Our other instrument is called Extend, and you can see it is a very large field of view CCD camera. So it's, I think the remnant people in the crowd will know that that's SN 1006 up on the top right. It's about 30 arc minutes across. So it's about the size of the full moon. So extend would have the ability to capture, you know, that entire remnant in one pointing. Again, it's not a high resolution spatial imaging instrument. It will have about 1.5 arc minutes or so resolution, but it will provide an extraordinarily large field of view that will be complementary to resolve, and in fact will observe the same. The resolve field of view will fit within the extend field of view. So if you're wondering what's going on outside of the object that you're looking at with resolve, you will have that data as well. The Xray mirror assemblies are also being made at Goddard. This is what one of them looks like. This is a quadrant of one of them. They are, again, nested shells. They are, you know, extremely small nested shells compared with the mirrors on Chandra. There are actually 203 shells in that one quadrant you see right there. So there's 200 per quadrant, then you make 4 quadrants, that's 1,800. Then you have a primary and a secondary, so that's 1,600. And then we have 2 instruments, so 2 mirrors. So that makes 3,200 mirror segments. About 25% of those don't pass quality assurance because they're all individually tested. So our mirror lab at Goddard has made about 4,000 of these mirror segments and has put them all together. And in fact, this is what it looks like when it's all assembled. I took these pics myself with my cell phone when we were out at the beamline one day, and the mirror was coming out. And so it's about, I don't recall exactly the diameter. Somebody might know better than I am. It's roughly 50 centimeters or so in diameter, and it weighs about 40 pounds or so. So very lightweight. You can literally pick this up by yourself if you wanted to. Extremely lightweight, relatively cheap mirrors to make. I mean, nothing's cheap in astronomy, but compared to the cost of other mirrors, this is a relatively cheap and quick process to make something like this when you don't have to have arc-second resolution. So, oh, I forgot to put this picture in. Yeah, I thought this was hilarious when I saw it on the box. Somebody stenciled on "Do not drop." I don't know if people were dropping boxes on purpose, but we take mission assurance and safety very seriously at NASA. So on to some of the science that we'll do with this. I showed this spectrum earlier. This is the Hitomi Spectrum of the Perseus Cluster. We were not yet up to full operating capacity on Hitomi. We still had, there was a blocking filter in front of the detector that's called the gate valve that had not yet been opened. It was planned to be opened. And if it had been open, and we will have another one on Chrism that will open once we get on orbit, the actual spectrum that we would expect to see at the soft X-ray energies is something like this. And so if you go back, the Perseus cluster doesn't dip down, at 2 keV. It's just that the blocking filter cuts off all of these photons below about 3 keV or so. If we remove that, we would expect to see something like this. So again, as wonderful as the Hitomi spectrum was, there's still a lot more science that we can do, even if we were to go back and reobserve Perseus, which we will. Here's another simulation. This is a supernova remnant. This is the remnant of Tycho, which actually turns 450 this year. It exploded in 1572. I put a box here that shows the approximate size of the resolve field of view. We're 3 arc minutes on a side, so we can tile across this and map the entire thing. But if you were to just look at a spot like this, you might see a spectrum that looks like this. And you might say those spectral lines look different than ones you showed before. They're much broader. Well, that's true. And that's because I intentionally, when I made this simulation, I intentionally broadened those lines by several thousand kilometers per second, because Tycho is expanding at 5,000 kilometers per second or so. So we'll actually be able to measure the Doppler broadening from the velocity of the overall structure of the remnant. We'll also be able to measure the thermal broadening due to extraordinarily hot gas there. And so this again is something that we have not been able to do for extended sources like this. So it'll be yet another dynamical measure of the remnant evolution. Here's a picture of M51. I chose a Chandra picture here for this. Again, there's going to be a lot of galactic science that you can do with stuff like this. how is the gas heated in galactic environments? Is there charge exchange in complex regions of emission? And so again, I made this. This is the actual Chandra spectrum of M51, and what Chrism will see will look something like this. So we'll have a lot more spectral information, of course, than we've ever previously had before. And when combined with things like high resolution imaging from Chandra, we'll get a much fuller picture of the science and the astrophysical processes that are going on in these objects. Here's another simulation. This is NGC 1365 and AGN. The XMM spectrum is shown up there on the top right. And then a Chrism simulation of what we would expect to see is shown on the bottom right. And we will not only detect the absorption features that are present there, but we may also detect scattered emission off of the outflow of the infalling gas that's falling into the AGN. So this will be yet again a new measure of the dynamics of an AGN wind. So if you want to read more about the science that we will do, the team put out a white paper a few years ago. You can find it on ADS pretty easily if you search for Chrism Science Team. It's only about a 25 or 30 page white paper, so we tried to make it as readable as possible, but it gives a lot of examples like the ones I just showed of what Chrism will do. And it's just meant to be sort of an introduction to the astronomical community of what you would expect to find for all manner of astrophysical objects when you look at them with a high resolution spectral imager. So we even put in some words about exoplanets. So we really are trying to cover everything that Chrism will possibly do here. So on to the mission timeline of where we are. As I mentioned earlier, the delivery of the calorimeter spectrometer insert happened in November of 2019. The white paper that I just showed you was released on archive in March of 2020. We made our final selection of our performance verification targets in February 2021, and I'll talk a little bit more later on about what the PV phase is, what the targets are. The NASA AO for the Chrism Guest Scientist Program will be coming out soon, probably in the next couple of months. And again, I have a slide on that a little later that tells what that actually is. The delivery of the Xray mirror assemblies that I showed you should be happening pretty soon. It was scheduled to happen in January, and then the Omicron variant, messed everything up. But we anticipate delivering those to JAXA relatively soon. We're still targeting a launch window of early 2023. And the start of AO1 observations will happen about 9 months after our launch. So 2023, maybe 24, somewhere around that time scale. An obvious slide that we have to include in these times is how has COVID affected us, and it has affected us a lot. Travel is still extremely limited for us. We had people in Japan as of November 2019. We had people in Japan all the time. They had to come home when COVID, first broke out, and we all, went into lockdown. There were about 4 months where we weren't able to travel at all. Then in July 2020, the Japanese government started allowing very small groups of NASA personnel to come over. Travel for those folks was extremely onerous, and generally had to quarantine for 2 weeks upon arrival in a small hotel room where basically they just got meals delivered 3 times a day to their door and they couldn't leave. That has slowly started to go down. In fact, I just heard this morning on a telecon that the government is considering removing the quarantine requirement for vaccinated people. But the rest of the Resolve team has been supporting remotely. So pretty much every night we have people that are up all night on Zoom telecons like this, watching people work and communicating back and forth as well as possible. I think it's been going pretty well. I think the IT tools have been working as well as anyone can expect. So I have not been able to go to Japan for these past 2 years because I'm not really a hardware person. But I certainly owe a debt of gratitude for all of those people who have and who have, quarantined for weeks at times. The work on the mirrors, as I said, has been going quite well. We expect to be delivering those relatively soon. And the science team itself, we hold every 6 months we hold meetings. We typically have been doing those in person, but of course, since COVID started, we've been virtual ever since then. So I mentioned earlier the performance verification phase. This is our version of the guaranteed time for the science team. It will consist of the first 6 months of observations after our 3-month-long commissioning calibration phase. The data in this PV phase are proprietary to the science team for a year period, and then they'll all be public. We have chosen these targets already. There are about 50 of them. They're online. I'll show you the website in a little bit if you haven't seen it. So you can go in and see if any of your favorite astrophysical sources have been included on this PV target list. We have purposely chosen a broad range of celestial sources for this, because the goal of the PV phase is to verify the performance of the instrument in all manner of the observing modes and all manner of targets and everything we can think of. So we have, though, come up with a way for individual scientists who are not on the Chrism science team to get involved in this early phase. And this is through something called the Prism Guest Scientist Program. And the way this will work is you can apply to join specific PV phase targets. You would only be able to, gain access to one target if you were selected for this. But this will be a competitive AO that will come out from all 3 agencies. If you're on this call, you will probably be applying to the NASA call, because if you're at a US-based institution, you'll have to. But basically, yeah, you look at the list, and if you see, gosh, I'd really like to be involved in the early data analysis for that, you can apply for that. If you are selected, there will be funding for you in that as well. And I want to emphasize, you don't need to be an expert in X-ray astronomy to apply. We will be seeking out people who are complementary to the expertise that's already on the science team. And that could be, you have theoretical expertise on something. It could be you have data from another mission on that. You maybe have ground-based data or something. If there's any way that you think that you can apply and add expertise to our science team, please consider applying for this. And as I said, this call should come out in roses very soon. After that, though, after our commissioning and our PV phase, the entire rest of the mission is in the GO phase. So we will run, just like Hubble, Chandra, Spitzer, all of these other missions, will have an annual call for proposals. You will write your best proposals, and they'll be competitively evaluated. And yeah, so NASA will get roughly half of the science time. It's relatively even split between JAXA and NASA, with a little bit going to ESA as well. But we anticipate this first call for AO1 to be released probably about 2 months after launch. In order to facilitate people writing their proposals, we are planning to have a small number, probably just 3 or 4 objects that are observed very early in the mission, probably right after commissioning. And we will be releasing some public data on those right away, so that you can at least see, what are the performance of the mission? How will this impact my proposal writing? And so this is going to be called the early release science targets. I don't have any more info on that yet because we haven't selected them, but as we get closer to launch, we'll make it public that these will be the early release targets that'll be put out right away, probably before even calibration. We will have TOO capabilities. We're not Swift, so we're not going to slew right away, but our goal is to have a turnaround on TOOs of less than 48 hours. I hope that once we get on orbit and figure out the mission operations a little better, that we can maybe dial that down a little bit, but our mission goal is 48 hours or less for TOOs. I think I've said everything else. We are planning on having some funding opportunities for laboratory astrophysics work as part of the AO. So again, stay tuned for that. And if you want to learn more about the mission, we have websites in both Japan and NASA. There's an ESA website as well. Probably better than trying to memorize these addresses. We've been around long enough now that if you just Google Chrism, these will be the first several sites that come up. On the NASA side, we have a public-facing site that's down there at the bottom right. The site that most of you will probably want to go to is the researcher site. That's where you'll find, response files if you want to do simulations and other documentation that you might need to write your proposals. So again, these are linked to each other. They're not hard to find. Just in closing, I wanted to say that I think high resolution X-ray spectroscopy, I think we would all agree it's a largely unexplored space. And I think that as we saw from the Hitomi mission, there's really a wealth of information out there about the universe that we haven't yet had the opportunity to fully explore. So Chrism is a general purpose astronomical observatory. We think we can make contributions to just about every area of astronomy. So please do consider us when you're, in the next couple of years, when you're writing, various proposals to think about getting into the X-ray spectroscopy world. We'll have some things like data analysis workshops coming up to tell people, introduce people to the software and tools that we use. So stay tuned on that. For those of you going to the head meeting in 2 weeks, we're going to have a mission status special session there, or splinter session there. So you'll hear, a lot of the stuff I just talked about, but we'll actually go into a little bit more detail on current mission status. On the Chrism guest scientist program, we have someone from headquarters who's going to be talking about that and the early release stuff. So it'll be a little bit more in-depth mission status update than what I've given here today. So please do consider attending that. I think it's Thursday morning at 10:30. And so with that, I think I will conclude and take questions from the audience. I think that's my last slide. Yep. So thanks.
Thank you so much. Wonderful. Let's really hope that it will go beyond the 38 days. Okay.
Yeah.
So we are open for questions. We have plenty of time, so don't be shy. Maybe I can read now a question from Dan from the chat. What is the data rate? How strong a point source can be observed with essentially fully energy resolution?
You mean how bright of a source? Is that the question?
The telemetry data rate and the flux of a point source that doesn't degrade the resolution.
Yeah, so the first one, I don't know the answer to the telemetry data rate. I mean, we'll have several ground passes a day, so I don't anticipate it being a problem of getting down the data. The bright source question is a good one though, and we do have a working group within the team right now that's looking into that. Certainly anything, if we point at the crab, we're going to be completely saturated, but if we can point at something, and I don't know off the top of my head, but it's of order, maybe 1/10 of a crab or so is kind of the point where we're okay, I think. We do have some mitigating, we have some solutions in mind that we think will mitigate. Obviously, we have some filters on board that give us factors of a couple. There may be ways that we can put a source, slightly off the detector, but still get photons from that scatter into the detector. So yeah, I anticipate this working group will actually put out a report at some point about exactly that before launch. I don't know the exact details, but I know it is something that's being very, very actively explored.
Thank you.
Hmm?
Thanks. Okay, there's a question from Pat.
Well, so Brian, just to follow up on what Dan asked regarding the telemetry rate with IXPE, for example, which does have regular passes as well, but they do have to interleave bright sources with fainter sources to be able to make sure that they can get all the data down from a bright source. So it might be worth just looking and seeing if that is an issue, because it impacts at some level the scheduling. Now those are longer observations on XP, so maybe it's not a deal, but I'm not sure.
Yeah, I'll ask around about that. It's not something that I've heard people raising as a big issue. So I guess the people who do think about that think they have a way around this. But yeah, I'll try to get you an answer on that and see.
Thank you. Any more questions? Please raise your hand if you have. I might ask one while people think. So about supernova remnant spectra, what is the capabilities due to this super spectral resolution? What is the capability of looking, for example, at interaction between non-thermal electrons and the ions in the shock regions? Can we, for example, constrain the amount of non-thermal particles, suprathermal or non-thermal particles there?
That's a little bit out of my expertise. I might turn that question back around to you. I mean, what would be the question, I guess, was what would be the spectral signatures that you would be looking for? And can we do that at these levels of accuracy? So I don't know the exact answer to that question, but if there is any sort of spectral signal that's produced by that, I mean, I think we would be able to see it. So is there a particular signal that you would be looking for there, like a line or a shape in the spectrum?
Well, I guess any modification from the spectra you would expect if there were no energized particle, energized electrons at all. I don't know what specific feature one will look for, but I assume if there is some interaction, one should be able to see something with this spectral resolution.
Yeah, I mean, I would certainly expect us to be able to see something. As I said, I don't know too much about that exact process.
Okay.
But yeah, I'd certainly encourage you to, if you do any models or something like that, to consider, you can pass a model through our spectral response file that we have available online to see if, see what it would look like when it was observed by Chrism. And those response files should already be online on our HESARC website for researchers. If they're not, let me know. But you can already start to do simulations using the detector response files that we have already.
Okay, maybe I have a topic for a proposal to submit.
Yeah, exactly.
Okay, so Brandon.
Yeah, hi. I want to know if there's any sort of, I'm guessing the answer is going to be no, but within the collaboration, are there any particular interests in the laboratory astrophysics side that are, preferred in some sense for people to explore, or things that people in the collaboration really want you to go after, or want laboratory astrophysicists to go after?
There are, and we actually, so we formed a laboratory astrophysics working group as part of the science team. And we actually, for the Astro 2020 decadal survey, when there was a call for white papers, we produced 2 white papers that came out of that team. So I would encourage you to go find those. I mean, I know they're certainly on archive. I'm trying to think how you would find them. They might have been published under Chrism's science team, or if you want to send me an email, I can dig them up as well. I have them or can easily find them. But Tim Kallman was the leader of that Lab Astra group, and Yella Kostra was the co-chair of that group. So yeah, they put a lot of work into those pair of companion white papers describing exactly the answer to what you're saying, where they think the areas of Lab Astra that need to be explored soon should be.
Thanks.
Thank you. I think there is another question from Dan.
Yeah, I was wondering to what extent you might be able to dither the satellite to improve the spatial information, and are you oversampling the mirrors anyway?
Well, that's a good question. I don't know if the operations team has looked into that yet. That's something that's fallen more on the Japanese side in terms of the actual spacecraft operations and whether or not certain observing patterns can be done. It might be possible. I can bring it up to the folks who are talking about this to see if that's possible. I have not heard anyone mention it yet, but it's also one of those things where I'm sure when we get on orbit, we'll be able to try out, other things beyond our standard observing plan to see if there are ways to improve something like that. As you can imagine, with a mission like this, there's a lot of hesitancy right now to, start going outside of the box. Given the history of this mission, we really just want to get it up, make sure it works at the base level first, then we can explore other things like that. So I'll I'll ask around about that, but I haven't heard anything like that yet.
You can just remind me how stably does it point, and what are the pixel sizes?
Yeah, the pixel sizes are 30 arc seconds. Our resolution on Hitomi, we got about 1.2 arc minute resolution. So our mission requirement is 1.7, but 30 arc second pixels. The pointing stability, I don't recall off the top of my head, but it's pretty good, but it doesn't have to be, you know, it doesn't have to be milli arc second if you have 30 arc second pixels.
Thank you.
Yeah.
Thanks. Let's see. Oh, there is a question from, I apologize if I mispronounce, Jay.
Oh, yeah, hi. Can you elaborate on the timing sort of performance of the satellite in terms of the timing resolution or dead time, that kind of stuff?
Yeah, the timing resolution, it's not a super high timing resolution. I think it's 100 milliseconds or so. I mean, it's definitely not, you know, nicer level timing resolution. It'll have a basic timing capacity, but it's not a super high resolution timing instrument. I might have had that. I don't remember if that was in my chart on the mission requirements of timing was in there. Let me see. No, I should update this chart though, because I do have the timing resolution somewhere. I don't recall it off the top of my head, but I think it's of order a few hundred milliseconds or something.
Thank you.
Thank you. Let's see, do we have more questions? Okay, I don't see hands raised or anything in the chat for now. I was just curious about planning. So within the first year or so, which would be the supernova remnants? I apologize for my question being biased. Which will be the supernova remnants? We will have data. So the
Yeah, so the
M6.
so the PV target list is online. I'll see if I can remember them off the top of my head. I know Tycho is going to be observed. I believe 1006 is on the list, probably not the entire thing. I think there are some select regions of 1006. Kepler supernova remnant, I believe, is a C priority PV target, which means if we can get to it, we'll do it. If not, we won't. It'll just be, you know, open for geo proposals.
For the Boccassé, for example.
Passé, yep. I don't know, Paul Pluchinski, do you remember any of the others? I think I hit the big ones.
W49B.
W49B, yep, that's one.
And Cygnus Loop.
Yeah, Cygnus Loop has obviously we're not going to map the whole Cygnus Loop, but there were a couple of specific regions in the Cygnus Loop where we were going to point at. So yeah, it's about half a dozen or so of those.
And 87A, of course.
87A, yep. Yeah, for us, 87A will be completely a point source, but it's certainly one that we're going to point at.
Excellent. Thank you. Okay, let me see. Excited from Chrism by Rudy. Okay, I don't see other questions or hands raised. So, very last call. If you have something, I think Jay still has a hands raised. So it's not a new question. Okay, all right. So if there are no more questions, just last encouragement to sign up for appointments, one-on-one appointments. There should be still plenty of room available for that. And if there are no more questions, we'll see you next week. Thank you so much for coming. Thank you, Brian.
Thanks, Brian.
Thank you. Yeah, thanks for having me.
Yep.
Look forward to seeing you all in person as soon as possible.
Couple of weeks.
Next week. Yep.
All right. Bye, everyone.
All right.